It's working? Okay. So, hello everyone. Thank you for joining us today. My name is Hidekazu Masuda from HIOKI. So, I am product marketing um, and responsible for the automotive segment for the test and measurement solution. So, today I'd like to talk about the how portable power analyzers are changing the way. Um, Let me check. Just a moment. Sorry. Now slide doesn't was removed. Yep, sorry. Give me a second. Yep, sorry. The traditionally the vehicle efficiency testing, that's usually the testing in the laboratory based like a chassis dynamometer testing. But now there are many automotive customers interested in the real world driving test. So today, in this session, I will explain why and then share the real world EV measurement example using our HIOKI's power analyzer. So first, let's talk about the both testing different situations for the vehicle testing. So usually the vehicle efficiency evaluation relies on the laboratory testing, but now the real world testing, real world driving testing, that's also important. So laboratory tests such as the chassis dynamometer test, that's provide the controlled and repeatable conditions. So they are very essential for the certification and fair comparison between the each OEM brands. However, the real world driving reflects the actual vehicle usage. So including the road conditions and traffic and weather conditions and of course the driver's behavior. So to fully understand the vehicle performance, the both perspectives are very necessary. The first, let's check the laboratory testing. That's a cycle-based test. So example, that's including the WLTP and SAE J1634. So this cycle defines the speed and profiles, and also the test durations and temperature conditions. So because all vehicles are tested under the same conditions, so cycle-based test that's provide a fair and standardized basis for the evaluation. And during the laboratory cycle test, so we continuously measure the vehicle electrical power and energy consumption, the whole system. So these electrical measurements needs to have the few key characteristics. The first, the measurement must be highly accurate. And second, they need to remain stable over the long test durations. So which can last for few hours, some hours, very long time test. And third, the measurement must be able to capture both power used for the driving the vehicles, as well as the power consumed by the vehicles actuary system, like HVAC system or other heat pump or compressors. So total the energy measurement is required. So the electrical measurement is a critical element of the laboratory vehicle testing process. So electrical measurement is required, of course, for the for EV cars, but that's not only for the EVs. So that's include the internal combustion engine vehicles and hybrid electrical vehicles and plug-in hybrid. So as vehicles continue to become the more electrified across the industries, so the importance of the accurate, comprehensive electrical measurements is only now continue to grow in the market. So now let's move to the real-world driving test situation. So why evaluate the vehicle in real-world driving? So some driving conditions are not fully represented in the laboratory test cycles. So real-world testing reveals the difference from the result obtained in those controlled cycles. So this real-world data is essential for the final vehicle validation and benchmarking against the competitor's product. So it provides more comprehensive understanding of how vehicles will perform under the typical driving conditions. So that's a customer's experience. By evaluating the vehicles in real-world environments, so we can uncover the insight that laboratory testing alone may miss. So this helps ensure that the vehicle meets the customer's expectations for the performance, efficiency, and overall driving experience. But however, real-world testing brings a new challenges. So when measuring the vehicle in real-world driving conditions, so there are some key measurement challenges so we must address. The first, the accuracy of the measurement must match the level of the precision required for the certification testing. So we cannot compromise on the data quality, so even in the dynamic real-world environment. The secondary, the measurement system themselves must be small and lightweight enough to be installed directly inside the vehicle without interfering with the normal driving operations. And thirdly, that we need to safely measure the voltage and current in the cars during the driving conditions. So these challenges are facing now, and then how we address these challenges. So that's the main topic for today. To get ready for our real world vehicle evaluation. So now we rely on the new HIOKI's power analyzer PW4001, the instruments that provide the accuracy and the simplicity and safety. So we need to capture high quality electrical data, even in the dynamic conditions of the on-road driving. So now that we have the right tools in the place, so let's take a closer look at how we use this power analyzer in the life situations, real life situations. So actually, our engineer in HIOKI, the last year, summer 2025, the HIOKI engineer conducted the real-world driving test using the PW4001 power analyzer. So we are testing the HIOKI's one company car, that's an EV car, that's a very well-known and mass-market electrical vehicles. So the vehicle was driven in a variety of environments in the Japan, the headquarters nearby, and we are testing in the urban areas and highways and mountain roads, while we precisely measure its actual power and energy consumption. And also, we also analyze how much power is consumed by the vehicle's air conditioning system. So that's also based on the measurement, real measurement data, so we collected. So today, I'll first explain how we implemented the measurement setup for this real-world EV evaluation. Then I will take a closer look at the actual result from this comprehensive testing. The slide shows the actual in-vehicle measurement setup. So we used for our real-world EV evaluation. The power analyzer is compact. That's a very lightweight. So weight is just 4.6 kilogram. So this makes it easy to install directly in the vehicles, as it can be powered directly from the 12-volt battery, external battery. So you don't need to bring the AC portable power supply in the car. For real-world driving tests, the operating temperature range is also important. The power analyzer 4001 is designed to operate from -20 to +50 degrees Celsius. And current sensor support an even wider range of -40 degrees to 85 degrees Celsius. So this wide temperature tolerance allows for the stable and reliable measurement, even during the most demanding real-world driving conditions. So this robustness of the power analyzer 4001 was the essential for the capturing accurate data and for in real-world testing. And then let's look at these photos. So now you can see the reality of in-vehicle measurement. So under the vehicles, we remove the covers, and then we can see the orange cable. That's the high voltage cables in the powertrain. But we have to access here for the measurement of the current or voltages. So that's a very challenging, that's very narrow space. So HIOKI, we are the measurement and test manufacturer. We are not automotive manufacturer, so we cannot cut or modify the high voltage cables. Of course, in Japan, such modification would also be considered illegal, and vehicles could not be driven on the public road if we modify the car. So we need to find a way to measure the current without modifying the vehicles and without compromising the safety. So this is where the HIOKI's compact high accuracy current sensors are effective. So this photo now, it shows the actual sensor installation points we used for our testing. On the left, you can see the DC current sensor installed directly on the high voltage cable running from the battery to the E-axle under the vehicle. And the right, other sensor is installed on the power supply line for the air conditioning unit. So thanks to this compact design of these HIOKI sensors, installation is very easy. So we just take a few seconds to clip on between these cables. If the sensor is too large, we have to modify the cables. We have to extend the cables. So in such case, it takes a very long time. So this sensors makes a shorter the setup time. Okay, and now let's talk about the voltage measurement. So measuring the battery voltage is very challenging than the current measurement. So current measurement, we can use the clamp type current sensors. That's electrically isolated. That's safety. But the high voltage measurement, we need to access the high voltage terminals. But usually these components were protected. That's isolated. So direct access on the battery terminal is usually not allowed. So again, so we cannot modify the car or battery terminals. So we try to find another way for the voltage measurement because for the safety reason. To solve this, so we use the battery voltage data from the vehicle CAN network. So the battery voltage is already measured by the BMS, battery management system. So on this data can be accessed through the OBD2 port or CAN bus lines internal the vehicles. So without touching any high voltage component, we can collect the battery voltage information from the car. So by combining the actual current measurement and the voltage from the CAN, so we can calculate the power safely and efficiently during the real driving. So this is a quite new approach enabled by the PW4001. This can help simplify the measurement setup and improve the safety in vehicle testing environment. And this slide shows the example of the OBD2 communication. So how we can get the data. So Power Analyzer 4001 can send a request to the car, and then the car OBD2 ID send the requested the information from the car. And then we can see like this, the high voltage battery pack voltage and the current and temperature. And also we can collect the vehicle speed information. So these are onboard sensors information from the car. So like this, by using this method, we are able to safely acquire the high voltage battery, and we can collect another information. However, battery voltage is not always available by OBD2. In fact, many automotive engineers tell us, so for example, in my test vehicle, battery voltage is not accessible through the OBD2. So that's true. Some OEMs or some cars, it's not output such information to the outside. So in this case, we can access the vehicle's internal canvas directly using the HIOKI's non-contact CAN sensors. So this is an alternative solution to access the internal canvas line. So as you can see in this image, the non-contact CAN sensor allows us to access the vehicle's internal CAN signal without modifying any of the existing wirings. So this makes the CAN-based measurement possible even when the OBD2 access is limited or unavailable. So we can tap directly into the vehicle's wiring harness. That's a CAN high and CAN low wirings without touching the metals. So we can tap from the insulation wirings. So no damaging the cables. So by using this, we can collect the CAN communicated data. But the important to note that the CAN sensor is only receive only device. So it does not allow for the bidirectional communication. So this is purely for the data acquisition purpose. But in other words, it means this measurement not affected to the car's ECU communication in the canvas line. So that's a real-world driving test. We don't make any effect to the vehicle's operation. So this is we can say this is very safety data acquisition method. At this point, there are two key questions, another questions from the automotive manufacturers. So the first, this CAN voltage measurement method is it really accurate, or we can use for the official power efficiency testing result for the certification requirement? So this is a very, very important questions. So to answer this, we say that's yes, but the measurement accuracy, guaranteed accuracy is main topics. So onboard sensors must have to meet the required accuracy level for each standards. So let's check the accuracy of the power analyzer and how we can guarantee the accuracy. The first, the PW4001 itself, that's fully meets the regulatory accuracy requirement. So it complied with the WLTP and SAE J1634. So it covering the voltage and current and power accuracy, including the current sensors. That's a combined accuracy. So, and we also guaranteed accuracy validate under the -7 degrees Celsius conditions. So the HIOKI provided the full accuracy information publicly. So you can rely on this accuracy. And next, let's look at the measurement method defined by the standards. So in addition to the direct measuring both voltage and current, the regulations also allows the use of the onboard vehicle data. So that means we have 4 methods totally. One is actual voltage and actual current measured. That's a traditional way. And another combination is a CAN voltage, onboard voltage data times measured current, or measured voltage times onboard current. And the last one is both onboard data, onboard voltage and onboard current. So we have these 4 measurement methods. But in the HIOKI considered 2 approach is the realistic for the power measurement in the EV testing. One is the traditional way, both actual measurement, voltage, current. And another recommendation is a onboard voltage, CAN voltage, and current sensor needs to use the current sensor, clamp sensors. So in these both cases, we recommend to use the current sensors. So next slide, I will explain why the current sensor is necessary. The standards actually that allows 4 combinations, but the current measurement should use the current sensors. Because onboard current data is often difficult to use the data calculation for the power because current changes is very dynamically. So it's bipolar. So driving the high current and then reduced to the almost zero, and then regenerative case, the current becomes another porous. So that's a bipolar operation, very wide range operations. So usually the onboard current sensors data is not high resolution, and the measurement accuracy is not enough for the power calculation. On the other hand, the voltage data works well. So battery voltage is measured by the BMS with high precision, high resolution. So, and battery voltage is nominally, that's a very stable. Like if the nominal voltage 400 volt, in that case, the voltage changes is between the 350 to 400 something. So that's only small changes compared to the current. So in our test case, we check the voltage measurement error, actual voltage measurement, and we compare the onboard voltage data. The difference is just 0.1%, for example. But the current measurement result, the error is 10%. So this is based on our experience, but of course, this measurement accuracy relies on the onboard car's voltage sensors level or current sensors level. So here are some comments we received from the automotive engineers after introducing this approach. So one key point was that the CAN data output reduced the effort required the data integration. And another comment was regarding the CAN-based voltage measurement. So this engineer wants to validate it through the comparison first, and then they gradually move to the vehicles, another vehicles. So this is the step-by-step procedure. So first, they will check the CAN-based voltage measurement is effective, and then they can switch to this approach. So that's the feedback from the US cycle test engineer. By the way, Roy, perhaps you could share some insight on how the automakers in Europe have reacted to our power analyzer measurement for the vehicle testing.
Yes, of course. Thank you very much, Hide, to give me the opportunity. When the PW 4001 was introduced in Europe, we visited several of the German car makers to introduce the PW 4001. And we especially talked to WLTP test engineers. Yeah, we got some interesting feedback from them, and some of them even, unexpected feedback. But the first one that I very much appreciate is that the PW 8000 or 4001 now recognizes the current sensors and automatically register the serial number of the current sensors. This is improving traceability. It reduces the chance of human failure, and it will save time in creating test reports. So that was appreciated very much. Another thing that was considered very positive is that the operating temperature of the PW 4001 was increased from -20 to +50 degrees, and especially at the low temperatures. This is very interesting for the car makers because they are able now to put the instrument in a climate control cabinet without our test chamber, without having to put a climate controlled cabinet for the instrument inside. This makes deployment of the instrument a lot easier and yeah, also makes it easier to change current sensors and that kind of stuff. So that was also very much appreciated. A third thing that was also mentioned, which was a surprise to us, was that the engineers appreciate very much that it's very simple to have a screenshot of the instrument now. It seems that when you are doing WLTP testing for South Korea, it is necessary to include screenshots in your report. And the PW4001 now has an individual button to give you a screenshot. So that helps a lot. And further, the shape and the size of the new current sensors makes it a lot easier to connect the current sensors to the vehicle on the test, making it possible to reduce the time of the setup of the vehicle. So in general, what we could say is that the PW 4001 has been received very positively by the German car makers, and especially because it is saving them time and and therefore saving them test costs. And that was the feedback that we got from our German engineers. So Hide, please continue again. Thank you.
Thank you for Roy. We are so very happy to hear that's response and feedback from the customers. So now let's go back to the main topics. So we are talking about our practical test examples. So real world driving test. First, we tested the vehicles in the mountain road first, and then after that, we drive the highways and we drive the city driving. And then during these 4 driving conditions, we measure the powertrain power consumption and air conditioning power. So let's see how we can collect the data. So this is the actual measurement data. The graph shows the calculated the energy consumption in watt hours. So over the time during the real world driving test. So this driving sequence was the mountain pass and highway driving and then city driving. The blue line represent the powertrain energy consumption. So the energy used to drive the vehicles. So to drive the motors. On the mountain roads, the energy consumption increases during the uphill driving first, and then in the downhill sections, the energy becomes reduced, becomes stable. So we expected this situation. The uphill used the many energies. And then highway driving, that's we use the large energies because the high-speed motor rotation and the driving, so simply the powertrain requires the more energies for the driving. And city area, that's very efficient and then less energy usage during the drive. So we can save the energies then compared to the highway or mountain pass. And then red line shows the air conditioning system. So this is our test is performed in the midsummer. That's very hot in Japan. So continuously the air conditioning working. So the air conditioning power consumption is increasing constantly. Not depends on the driving situations. And the green line represent the regeneration power. In the uphill, the regeneration doesn't happen, but the downhill, it starts to generate the power in the downhill driving. And that means a charging to the battery. And the highway, that's also generate the regeneration in the driving. And then the city area, that's also generate the energy during the drive. The white line, that's the total, the power consumption. So this becomes lower than simple drivetrain powers because we are generating the power during the drive. And next, this summarizes the result in the terms of total energy consumption and energy used per distance in watt-hour per kilometer. As we expected, the mountain driving shows the highest energy consumption, so due to the elevation changes. On the highways, the measured energy consumption per kilometer was lower than the catalog specification. So measuring vehicle performed more efficient than we expected. In the city driving, the energy usage is very efficient. So clearly we can say the EV car is very useful, it's very suited for the urban driving situation by comparing these data. And this slide now it's summarized the regenerative energy and used energy and actually power consumption. So over the entire test, the total powertrain energy consumption was approximately 11 kilowatt hours. Of that, about the 40% was recovered as a regenerative energy. And at the same time, the air conditioning consumed a significant amount of power. So that's almost 23% of total energy consumption. So the result that's indicated that extending the EV driving range requires both high regenerative performance and efficient powertrain driving, and also the reduced actually energy consumption like air conditioning system. So by combining this technology improvement, we can extend the drive range for the EV cars. So yeah, that's a very interesting result for us. And then we learned if you are driving the EV cars and then are a little bit far from the charge point, so in that case, we should turn off the air conditioning first, and then probably we can extend the driving range to reach to the next charge point, we guess. Before close that, I would like to briefly introduce the measurement instrument used in today's our practical test examples. So the power analyzer 4001, that's very good for the real world driving measurement. So power analyzer 4001, it's a portable high accuracy power analyzers and designed for the laboratory and real world testing for both. So it supports the high speed data update and CAN and CAN-FD communication. So importantly, this power analyzers, now we can drive using the external power sources from the DC power battery. So this is very easy to integrate in the EV car testing. And I think that some customers already know the HIOKI is the old power analyzer PW3390. So this slide shows the simple comparison between the old designed power analyzer and new HIOKI's power analyzers. So this power analyzer we launched in the last year, October. That's very new equipment. So we can provide the very high accuracy than before. And also we extended the operating temperature range, so we can guaranteed temperature range is expanded. So you can put in the chambers and in like test chassis dynamometer testing, I think you are putting the power analyzer in the cabinet or outside of the chambers, but then now you can simply put that next to the car. So you can simplify the wirings between the car to the measurement. And the new feature is a CAN communication support. So we have so many the update from the old one to new one. And then, but today I'm not deep dive into the specs. So please ask to our sales teams if you want to try, or if you want to interested in this product, you can check on the website, the datasheet. To close, let me summarize today's session. So the three key takeaways I have. So one is the real-world driving test requires the lab level accuracy for the fair comparison between the lab testing and real-world driving test. And second, the smaller and easier installation of the current sensor is very important for the real world testing for the cars. And also the CAM-based voltage measurement is a new approach, and we provide new test solutions to simplify the voltage measurement of the cars. That's a very safety and simplified test setup. So that's all from my side. So I hope the session and our test example was useful and give you some practical ideas for your own testing. Thank you very much for your time and attention. And then now I'd be very happy to take your questions. But before that, we want to ask you some poll questions from our side. Roy, can you start
Yes,
the poll
yes, yes,
question?
that's correct. Hide, thank you very much for the explanation and the presentation. Before we're going to start with the Q&A session, we have the webinar survey, and I would like to ask you to just briefly take a short moment to fill out the questions. And after that, we will continue with the Q&A. And fortunately, there are already a few questions, but still, if you have questions on your mind, don't hesitate, put them in the Q&A box, and then we will take care of them in a minute. Okay, thank you very much for filling out the poll. We will continue now with the Q&A, and as I mentioned already, we have already a few questions. Let me first start with the first question. Just putting the clamp on the orange wire is enough to properly measure the current flowing through the wire? Is the impact of the shielding not affecting the result? Hide, please.
Yes, I can answer this. So actually, the shield current is another measurement challenges. Yes, shield current through the leakage. Yes, and then it caused the measurement errors. So that's a real situation. So in that case, we had another measurement approach to address this. So we called it the double clamp method. So usually we measure the only high side, one clamp, but by measuring the low side, so we can comparison between the high side current flow and the low side current flow, including the shield current effect. And then we can, by calculating these data, we can estimate the shield current effect. So, but in that case, we need two channels for the accurate calculation, except the shield current effect.
Okay, but normally WLTP testing that we are doing with this kind of test, they are DC cables. Are they always shielded?
Always shielded, and
Okay.
usually automakers make a special assembly for the cables to remove the shield current.
Yeah. Okay. Thank you. Then second question is, if we work at -7 degrees, is there any time limitation for the PW4001? So is there a time restriction using it at -7 degrees Celsius?
Time limitation. time in the -7 degrees?
Yes.
We don't specify any time limitation in the -7 degrees Celsius. So we simply guarantee the operation in -20 degrees Celsius. So
Yeah.
that's very not
So,
effective, not
so in
effective.
general, we can say that there is no time limitation. The instrument is
No.
tested to work at these low temperatures. Okay. Then there's another question. There's another question about the shielding, but we already covered that one.
Mhm.
We also have how could you ensure the synchronization of the CAN measurement with the current measurement?
Yep. So in the DC power measurement of the EV cars, so DC power is of course, that's a battery current. That's a DC. So our analyzers, the calculation timing is every 50 milliseconds. They usually, so that's a regulatory required. Traditionally, they are using. So time synchronization between the CAN voltage and the current measurement. Actually, in the timing has measurement sampling is different, but in our test, our experience of the test, the actual voltage measurement result and the CAN voltage acquired data's difference is just 0.1% orders. So in that case, we can say the voltage, the CAN acquisition is not the big effect for the measurement result. And the current measurement also that's a real-time measurement. So we have the not so much difference in the synchronization each others.
Yeah. Okay. Thank you very much. Regarding slide 12, in on-road testing with the current sensor below the car, how do you put the cable of the current sensor inside the car? Wouldn't it touch the ground and damage it?
I think this right. Yeah.
Yeah, I
So
suppose so. Yeah.
in this case, we take an undercover of the Tesla, that's the EV cars, and then we can find the orange cable like this, and then this is the zoom out the orange cable part. So we have the two wires here. That's the high side, high voltage cables, high side and low side, and then we simplify the clamp our current sensors between these two cables. Is that correct answers to this question?
Okay. But how do you, the instrument probably is inside the car. So how do you get
I
the
see.
current sensor connected to the power analyzer?
Yeah, I can understand. So after clip the current sensors, we close this under panel, and then we simply the current sensor cables through the car's window. We make a space between the windows and then put the cables inside the car, and then the power analyzer itself, it's inside the back sheet. So
Okay.
mm,
That's clear. Then we have another question for the AC consumption measurement. Will it be needed special current and voltage probes? Or can we use the normal BNC current probe for the high voltage battery? We need one of HIOKI. On the terminals are special from HIOKI, not BNC. Yeah, no, our current sensors have a dedicated connector. And normally we don't use the BNC connector, which probably is not on the instrument at all anymore. In the past, it was with the 3390, but it's not possible to connect the current sensor with a BNC connector to the PW4001. So we can only use dedicated current sensors. And for AC consumption measurements, it's not necessary to use a special voltage probes because the voltage inputs can handle both DC and AC and can go up to 1500 volt. meaning that normally it's not necessary to have dedicated fault probes. Have you anything to add, Ide?
Yep.
No?
Thank you for right. That's
Okay.
great.
Okay, then there is that one we have basically covered. Do you have a database of OEM CAN? Is it just measure? Is it just measure, or you can send signal values and can activate some options? Could it be possible to add CAN measurements to the PW3390? Well,
Yes, I will answer this. So first, the database of the OEM CAM. So we don't have the OEM the CAN database file. That's usually we said DBC file. So we need a set DBC definition for the CAN IDs to transform to the parameters. In our test case, we use the OBD2 communication. So OBD2 communication is the very public information for the dealer maintenance service. So we can collect the OBD2 communication definition DBC file. But the internal vehicles can communication requires the each OEMs should have the individual DBC files. And the CAN measurement is only for the power analyzer 4001. Unfortunately, 3390 cannot support the CAN communication.
okay. Thank you, Hide. And then we have another question. That's basically a follow-up on the question that we answered before about the current sensors. It's mentioned that the dedicated current sensors probes are quite expensive. But yeah, to be able to measure the current accurately, these current sensors need to have a high accuracy. And the normal current sensors with basically a BNC connectors normally have an accuracy of around 1 or 2%. Whereas the HIOKI current sensors, they have an accuracy which is much higher. And the latest current sensors that we use for WLTP testing even have an accuracy, a base accuracy of 0.07%. And that's necessary to be able to fulfill the requirements of the WLTP. And that's why it's not possible to connect a regular current clamp with a BNC connector. All right. Well, then I think that we have. There is another one coming in. Can you broadcast the real-time calculation of the third-party data acquisition hardware through CAN bus? Yeah, the CAN bus has a double purpose basically. If you don't use the CAN bus to get data acquisition from or CAN information from the car, you can use the same CAN interface as a CAN output, and then you have the ability to export measurement data to third-party data acquisition systems in CAN format. Yeah. Okay. Then at this moment, we don't have any open questions, but please feel free if you still have a question, put it in. We will wait a few moments before closing the Q&A session. So please go ahead and answer. We're still here. We're live. We can answer your question. So please use the opportunity. Now, Hide, I think that we have made a clear presentation and answered the questions that the people had. So I would like to thank everybody for participating in the webinar. And yes, if you have any further questions, please don't hesitate to contact us and to contact our local partners. And yeah, we hope to see you in a next event or a next webinar of HIOKI. All right. Thank you very much. Bye-bye.
Thank you so much, everyone.